And I hope you enjoyed your weekend off. I did add homework 10. It's three problems that's due Friday of this week at midnight. And so that's out there. And when we left off on Friday, we were talking about barriers and tunneling. And so I want to get back into that. After I just say a few introductory things, maybe 5-10 minutes, we're going to break up into groups and solve two problems. The reason you got the weekend off, I think, is because I've assigned these problems to people cold without any help. And it's frustrating because of the size of the numbers and the fact that you may or may not own a calculator that'll do a hyperbolic sine. And so I have to show you a few tricks. Now, you can always get this done with Symbolab and MathNet and Wolfram Alpha. And Wolfram Alpha is now gone to the bottom of my list since they're showing themselves to be kind of greedy, trying to sell you the pro version. But that is one way to evaluate a hyperbolic sine or hyperbolic cosine if you need to. But still, the size of the numbers you're going to deal with may cause your calculator to not work. Many calculators won't calculate a number greater than 10 to the 33rd or a number smaller than 10 to the minus 33rd. And so if that's a calculator limit you have, you're going to have to figure out tricks in order to do numeric calculations for very big or very small numbers. So that's the first frustration. Second is what I already mentioned, the fact that you might not have the ability to do hyperbolic sines, which you need to do the tunneling problem. All right, so let me share my screen with you. And this will be just a quick overview of what we talked about on Friday with respect to the barrier problem. And hopefully you're seeing a PDF rendition of my PowerPoint notes. And remember, we were looking at something like this, a barrier of some height in joules, V0, okay? That's a terrible looking arrow. We're starting off just great with penmanship here today. And that's a V. Let's move the V0. And we've got a particle coming in with some amount of energy, either some amount of energy E greater than V0 or some amount of energy E less than V0. And so here's the two cases that we're going to look at, okay? And as you may recall, we defined a reflection and a transmission coefficient based on the solutions to Schrodinger's wave equation in the three regions that we labeled 1 and 2 and 3. And we looked at the solutions for that. We think that this first equation right here, that's the particle being represented by a wave moving towards the barrier in region 1. The second one here is the particle being reflected off of the barrier, which happens even if the total energy of the particle is greater than the total energy of the barrier. You still get a reflected particle. And then F here would be a particle that has transmitted beyond the barrier, okay? And that's the wave function that we believe solves Schrodinger's wave equation for that possibility, okay? And so we're going to define the transmission coefficient as the probability that it's moved past the barrier, hence the F right there, and you multiply by your complex conjugate merely to get rid of that piece, right? And we're pretty much going to stop with that. You could calculate the reflection coefficient, which would be b squared over a squared. These things are like gains, what you get out versus what you put in, or efficiencies, what you get out versus what you put in. A transmission coefficient or a reflection coefficient follow that same pattern, okay? In any event, the reason we only need to get the transmission coefficient is we recognize there's only two possibilities here. It either transmits through or it reflects back. It's kind of like flipping a coin. Either you get a head or a tail. We discount the possibility that the coin lands on its edge, for example, and there's no possibility that the particle comes in and somehow gets lost. We don't have annihilation happening here. So it either reflects off or it transmits through. And so the probability of those two has to add up to be equal to 1. We favor finding the transmission coefficient. Then if we need the reflection coefficient, we just subtract it, the transmission coefficient from 1, and that must be the reflection coefficient. And that's why we said, oh, look, my pen turned off. That's why we said this here. Okay, so here's our equation, right? And the only thing when you do the math, and by the way, the extra credit it was, if you recall, looking at these solutions to Schrodinger's wave equation in regions 1, 2, and that was supposed to be a 3 right there. I don't know if it got lost or if it was just a typo right from the beginning. Okay, looking at those 3 wave functions, which solve Schrodinger's wave equation, you can see this is the one coming in, this is the one being reflected, this is the one that ultimately gets transmitted through. We evaluated these wave functions with an eye towards the boundary conditions, that at the edges of our barrier, the wave function and the first derivative of the wave function, basically the slope of the wave function, had to match. We said the slopes couldn't be discontinuous, right? Not allowed. And so we looked at those 4 boundary conditions and we arrived at 4 equations, which you can work on to eliminate everything but F and A, because those are the 2 coefficients you need to get a transmission coefficient. 4 equations, you got to manipulate them to eliminate all the variables B, C, and D, and only have F and A left. And if you have F and A left, you can figure out what the transmission coefficient is, because it's F squared over A squared. And so for 5 points on classwork, I challenge you all to prove that what you get is, stop rolling, is this equation right here. If you don't want to do it, that's fine. You'll see it again in quantum mechanics class. The only thing I want to remind you about this is that it is a reciprocal right there. This transmission coefficient is the things in that square bracket raised to the -1 power. Okay. And so that is a little bit problematic, I guess, because I'll see people forget to take the reciprocal once they're done finding 1 plus that ratio V0 squared, the height of the barrier, times sine squared of the wave number K2 times L, the length of the barrier, right? Because it's 0 to L, over 4 times the total energy minus the potential energy, which is the kinetic energy. Okay, so people forget to take that reciprocal. Don't forget to do that. Check your units. But hold it, wait. Transmission coefficient, dimensionless units. So units may not save you here like it often does. In any event, one other point I want to make here is that if you know what a sine curve looks like, and hopefully everybody does, and then you know what the sine squared curve looks like, it does something like this, right? As a function of K and L, the sine squared of K times L is equal to 0, okay? And so remember, it's the reciprocal that we really are looking at here. There are places where you get a large value of sine squared, okay? And there are places where you get 0, right? And so you can see that the transmission coefficient might oscillate a little bit on you based on the fact that the sine squared oscillates on you, okay? And that's kind of an important point, I guess. Is it possible to have 0 transmission? I'm trying to figure out a way, and I don't see it, because you've always got that 1 that you're adding on right there. Okay. Is it possible to have an infinite transmission coefficient? No, but you have to see that it's going to be oscillatory. It doesn't like decrease with the width of the barrier, for example. There will be different barriers that favor transmission more than others, and it isn't like a wider barrier causes less transmission, which might be the intuitive thought. And that is because of the nature of that term. Now, here's my advice. My advice is to remember what K is in region 2, and K is always in these Schrodinger wave equations twice the mass times some type of energy. In this case, it is the energy minus the potential energy, right? The height above the barrier over h bar squared. My advice when you're doing this calculation is always to figure out what K2 is first, because you'll have those numbers, okay? And then figure out what K2L is, and it's going to be a fairly unique, bizarre, big or small number depending on the relative size of your barrier and um, and and I guess the value of the difference in the energies, what the kinetic energy is. Okay, so do that first, and then finally plug that right in there and turn the crank on it. And so that's what one group is going to get to do. All right, that's one of the problems that you're going to have to do, simply evaluating that transmission coefficient, remembering those pieces of advice I'm giving you. That works really well for this case, right? Where the energy is greater than the energy of the barrier. It gets a little bit slippery when the energy is less than the energy of the barrier, okay? And you get a different set of equations. And in that particular case, we get not, the equation looks very similar for the transmission coefficient, with one exception. You swap out the sine squared of k times x. We've relabeled what the wave number is in the barrier. We've called it kappa. You may remember in the finite square well, in this analogous case, we called it alpha instead of K2. Has the same meaning. Why our author changes to a completely different letter is an interesting question. But the point is, it's a hyperbolic sign, not a sign that is squared in the equation. Okay. And I feel obliged because I know a number of you are going into differential equations next semester. And Dr. Kem tells me that I think 3, maybe 4 of you want to take the E&M class next semester as well, while you're taking differential equations. And the issue, of course, is Dr. Kem's going to need you to have a little bit more proficiency with differential equations right off the start. And so I got to give you just some big picture differential equations that physicists need to know. And so I want to start with this right here. If you get an equation that looks like the one that I'm showing right here, okay, a second derivative plus some constant, which we always call k, although sometimes we'll call it alpha or sometimes we'll call it kappa. But when there's a plus sign right here, we usually call it k squared, because the solution is either a cosine and a sine with appropriate constants and k times x. And oh yeah, by the way, I hate this notation. That second derivative there is with respect to x, and that's why I've got an x right there and right there. Or it could be a complex exponential. Okay, the reason that works is because of Euler's identity. It could be either one of those because Euler says they're equivalent. You know, I was looking through my notes as an undergraduate, actually my textbook as an undergraduate. I still have my undergraduate differential equations book. That's kind of the course where I became aware of the relationship between a sine and a cosine. Okay, and it is fundamental to much of what we do in physics, so you have to know that. The reason that these two equations are both solutions is because if you take Euler's identity, notice this is for a positive ikx up there in the exponential. If you have a negative sign, all it does is change this. And so I can take these two forms of Euler's identity, I can add them. You can see the signs will cancel because one's positive, one's negative, and I'm left adding them being equal to twice the cosine of kx. So the relationship between a cosine and a complex exponential is established with that definition. It's e to the I kx plus e to the minus I kx over 2. That's what a cosine is. Had instead I subtracted the two forms of Euler's identity, I could have established a relationship between sine and complex exponentials. And there's two differences. Of course, I'm subtracting now these two equations. That's why I drew the line, by the way. That line right there is because I'm either adding or subtracting the two things above. Add them, I get the cosine. Subtract them, I get the sine. Notice by subtracting them, I get that. The cosines cancel in that case. The sines add, but it's 2i. So the definition of a sine in terms of complex exponentials is e to the ikx minus e to the minus ikx over, in this case, 2i. So you can see it's a little bit different from the cosine. And that's why either of those two solutions is allowable. Now, you may wonder where I'm going with this, because the other possibility, besides this differential equation right here, which has a name, at least as a acoustician in the physics community, I refer to it as Helmholtz's differential equation. I mean, when an equation is so well known that it gets a human being's name, well, in that case, we just memorize the solutions as physicists. The mathematicians will redo Helmholtz's work for us, but we're just going to buy Helmholtz got this right. Other people give it a different name. Helmholtz was an acoustician. I'm an acoustician, so in my discipline, we name it after him. But there are other differential equations you'll run into. Bessel's differential equation, Legender's differential equation, okay? The name of the solution then becomes a Legendre polynomial or a Bessel function, okay? The solution to Helmholtz's differential equation are sines and cosines or complex exponentials, and according to Euler, they are equivalent by his identity. Okay. And so in the same way you might have known about trigonometric functions when you took algebra, but it wasn't until you took an advanced algebra or trigonometry course that you knew what to do with it. You do want to be careful about complex numbers, because I'm sure everybody has heard of the square root of -1, but knowing how they work their way into the mathematics is important as you move on into math and physics courses. All right, here's where I'm going with this though. And there is a point, it's just long-winded. What if I change from a positive sign in Helmholtz's differential equation to a negative sign? Okay. And again, this k here, k squared, sometimes we'll call it alpha squared, sometimes we'll call it kappa squared. We give it different names. Okay. The solution is not a sine or a cosine or a complex exponential. The solution is a hyperbolic cosine and a hyperbolic sine, or a real exponential that is either positive or negative. And so the equivalent of Euler's identity for the real solution, and I don't know what to call it when it's a negative sign right here, but it looks a lot like Helmholtz's differential equation. It's just sines, hyperbolic sines and cosines instead of sines and cosines, which we know a whole lot about. I guess the equivalent to Euler's identity is that e to the kx is equal to the hyperbolic cosine of kx plus the hyperbolic sine of kx. Notice no I there. If I wanted to go e to the minus kx, it would be hyperbolic cosine of kx minus the sine, hyperbolic sine of kx. Okay, great. If I'm just going to subtract them this time. Hopefully you can see I can add to get a hyperbolic cosine, but I need the hyperbolic sine because you may not have a calculator that does that for you. So that would tell me if I subtract these two, e to the minus, e to the plus kx minus e to the minus kx. Well, these guys will cancel, and I'll get 2 times the hyperbolic sine of kx. And so it appears to me that the hyperbolic sine of kx is equal to e to the kx minus e to the minus kx over 2. And if you don't have a calculator that'll do hyperbolic sines, and many won't, if you got that cool TI Inspire, you plug the money into that, you can do it. But otherwise, the rest of you, I know everybody has a calculator that'll do exponentials. And so when you're doing the problem where you need the hyperbolic sine to calculate the transmission coefficient, that's one way to do it. I'll even go one step further on this, okay? Because remember, and I got to get to the right page in my notes here, for the case where energy of the particle is less than the energy of the barrier, we said that the transmission coefficient is equal to 1 plus the potential energy barrier height squared times the hyperbolic sine squared of k times L. I've replaced x here with 0 X becomes equal to L, the barrier width, okay, divided by 4 times the energy of the particle times the kinetic energy. Well, I inverted these in order to get um, a real number. So instead of being E minus V0, since V0, oops, I got rid of my division line there by trying to erase. I turned this into a positive number by going V0 minus E, because in this case, V0 is greater than the energy of the particle, right? That's what we said. So I turned it into a real positive number there just so that I can work this right. And that's taken to the -1 power. All right, here's another reason why you really want to, and in the equation where the energy of the particle is less than the energy of the barrier, our author has made one other notational difference. He turned that K right there into a Greek kappa. And of course, the Greek kappa looks just like K, twice times the mass of the particle, only we went the potential energy minus the total energy divided by h bar squared. Again, so that we keep this positive so that kappa is a real number. Okay, and that was what we did on what we talked about on Friday anyway. Again, I would recommend figuring out what kappa is and then multiplying it by the width of the well. And here's why. Because if kappa times L is a big number, and it often is, okay, the relative sizes of things we're talking about here, kappa looks like a wave number, so it's inversely proportional to a wavelength. If the wavelength is small, kappa is big, okay? So then I want you to look at what happens to the hyperbolic sign in the case where kappa times L, which as I've written in Euler's identity is kappa times X, because X is equal to L in our equation right here. What happens when this thing right here is big? Well, if kappa times L, that exponent right there, is a big thing, doesn't that term right there become very small? So much greater than 1. If kappa times L is much greater than L, a big number. And this is like small angle approximation. How small is small? Big kappa times L. How big is big? Well, E is 10, right? E to the minus, I'm sorry, E is 2.7. If I raised it to say 10, that would be 1 over 2.7 raised to the 10th power. That's a pretty small number. So, hey, 10, how's that? That's how big it has to be big. I guess my point is, look what happens to this equation in the case where K times L is a very big thing. Well, it looks like the transmission coefficient can be written 1 plus V0 squared, replacing this with just E. Slide back up right there so you can see where I'm getting this from. I'm looking at the rest of the terms here. It would be E to the plus kappa times L over 2 squared. That replaces the hyperbolic sign in the case where kappa times L is big. Okay, all that divided by 4 energy and the difference between the barrier height and the energy of the particle. Okay, and this is all raised to the -1 power. Now, if kappa L is a big number, such that I can replace it just with that real exponential, how big do you think this second term is compared to 1? And the answer is it's going to be much bigger than 1. So simply adding 1 to this thing is ignorable. So I'm just going to ignore that. Okay. And then you get a much simpler equation, I think. Let's see. If I could ignore that, all I have then is that the transmission coefficient would be, now watch all the terms here. I've got 4E, the total energy of the particle, the difference between the barrier height and the energy of the particle. All that divided by V0 squared. And then I've got E to the square that, it'll be 2 kappa L. And then that's divided by 4. And I've taken care of my reciprocal right there. More conventional to write that. Let's take the two 4s, put them together. 16 E times the difference in the barrier height and the energy of our particle over V0 squared. And then I guess I can bring that exponential up, minus 2 kappa L. All right. And you could manipulate a little bit further if you want. You might factor out a V0 from this and cancel one. But this equation right here may be a whole lot easier to put into your calculator than that equation right there. Now, I spent way too much time talking about that. So now it's time to break up into groups. You get about 10 minutes to work the problem, and then we have to go on to something else. Here are the two problems that we're doing. Zipping through to my worksheet here. Yeah, come on. End of the semester, too many things. Barriers and tunneling, there it is. And 4 of you will work on the first problem. And notice here that the transmission, it's a 5 MeV alpha particle. Okay, and the barrier is 2.5 MeV. And so the way I interpreted that, let's make sure I agree with what I'm about to say here. I interpreted the 5 as being the total energy. Sometimes people say things like that, they mean it's the kinetic energy. When I work my answer key, I said 5 MeV is the energy, and the barrier is 2.5 MeV. So that's a case where the energy of the particle is greater than the energy of the barrier. And you got to find both K2 given right there, and then plug it in and get the transmission coefficient. I would hope your intuition would tell you that since the energy of the particle is twice that of the barrier, there's a pretty good probability that the particle will transmit by. Classically, you'd expect it to be 1. Quantum mechanically, it'll be something less than 1, but still a pretty good probability of success that the particle is going to get by. All right, then the other half of you, unfortunately, you'll get what I think is the harder problem right here. Okay, now you've got a 5 MeV alpha particle, but your barrier is 15 MeV. And so you need to do the same thing, only you'll be doing the calculation to get, why is it my pen not working? There it is. You got to get hyperbolic sine. And you might find that the equation I simplified to might be an easier way to do that, a hyperbolic sine, than actually plugging it into your calculator. And of course, pay attention to the fact that your calculator may overload if the number's too big or too small. And you need to carry enough significant digits so that you don't inject large error into your answer. My hope is that your intuition would tell you that the probability that this alpha particle is going to get through that barrier is fairly low. Classically, should be 0. Quantum mechanically, there will be some probability, just like that kernel I showed you, actually general trying to get through the wall into the next room. Probably such a low probability it's not going to happen. All right, so I'm going to give you about 10 minutes, and then we'll come back and we'll meet on these. And so the first thing I got to do is breakout rooms, break up into groups. And Amaya, Anaya, Justin, and Max, you're doing the first problem. I think you won. You got the slightly easier variant. Prince, Sam, Seed, and Shneha, you're doing problem 2. See you in about 10 minutes. I'll be jumping back and forth.
H bar. Anyone got that?
Eh,
It's 5 times. Wait, I can do it.
The only thing I'd tell you to be careful about, that 5 is 5 MeV. The 3727.38 is also MeV, right?
Yep.
And H bar you'll often find in units of EV. So just be careful about that, okay?
Okay.
It's 136.52 divided by H bar.
Say that again.
136.52 divided by H bar.
H bar, and this is MEV.
Over C.
Now hold it. That one other thing, isn't that over H bar C squared?
C squared.
Actually, H bar C, I'm sorry, because it was under the square root sign, right? Because your MEV was MEV, your mass of your alpha particle was MEV per C squared. And so you needed a C squared under the radical and a C in the denominator. Now, my best constant for you on H bar C, H bar C here is 197.33. Now, here's why I said be careful. EV nanometers. Okay. And so your units will initially probably be inverse nanometers, but you got MeV here, and the constant is EV, which isn't too bad. That's just a factor of 10 to the 6th. I'm okay with leaving it in radians per nanometer, because if you look, your barrier width is it's 10 to the minus 14th meters, which you can write as a nanometer and cancel them without any problem.
So I got 691,836.
691,8 sounds good. I got 821, but 691 is 6918. Yep.
Yep.
And now put units on that. That's inverse nanometers, right?
Yeah. So
radians per nanometer, really. But if you want inverse nanometers is fine.
Yeah. Nanometers. Close enough.
-1. There you go.
Yep.
Yep. And now multiply by L.
Times L.
Which is what? 1.3 times 10 to the minus 5th nanometers.
Yep.
If I converted that right, and then plug all of that into T. Looks like you guys are on the road. I think you should be fairly successful with that, because I think most calculators will do the sine squared of K times L pretty successfully. So I'm going to go see the other group.
Okay.
Gonna get all right. Then we have E equals.
All right. Hey, before I get any further, let me stop you on your kappa. And here's what I think. Here's the issue I think you got. And the other group sort of did it too. And so just be careful about this. Remember, this number here for the alpha particle was per C squared, right?
Mm-hmm.
So you had to multiply by C squared in the numerator, which is under the radical. And so that means you have to multiply the denominator by C as well. So
I think I was a step ahead of you on Friday.
All right.
How does this make you feel?
That's good. That's good. So yeah, that now, but this is already, as soon as you wrote this as 3727, that's MEV per C squared, and that cancels this right here.
And then.
And this number right here is about 197 EV nanometers.
But I think I did this for problem 1, but it should be the same thing.
Yeah,
right?
yeah. So scroll on up, and so I think, and I'll get rid of my etchings right here. So I think that exactly your denominator needs to be H bar C, not just H bar.
Okay.
Why did we multiply it by C? I still don't understand.
Yeah, I think this is gone as soon as you just wrote MEV right there. Right, and you got MEV right here. So that MEV that used to be mass is MEV per C squared, right? So it cancels that.
This one is EV nanometers.
Yes.
But again, like
So
I said, like I generally don't get why are we multiplying it.
I think to make the numbers
Oh.
work out easier, and you can, I think the units are more understandable if you multiply by C in some cases.
Yeah, absolutely. Because remember,
With this.
if you're going to use 3727 right there, that's 3727.38 MEV per C squared. It is not just what a lot of people do, write MEV. And so this is a beautiful number right here, but it is units of MEV per C squared. So you've got to make it MEV. And the way you do that is multiply the numerator and denominator by C.
Is everybody
now what do you
happy with
get?
this?
Wait, so the units of kappa are defined, and to make the units properly work out, we need to multiply by C.
Yes.
Okay.
How
What
to get
unit
rid of
is kappa supposed to be in?
The units of kappa are just like units of K. It's an inverse length. In this case now, okay, and this is why I'm a little bit worried that you still are hanging, you got this C hanging on outside, because I think you're missing my point.
It
This number
cancels
right
in the
here,
units.
canceled, right? It canceled with the units on
Yeah.
mass. So now you're good. Now you can put that number in your calculator and look what you're going to get. This is now units of MEV. The thing in parentheses here, that's got units of MEV. So you've got MEV squared, but underneath the square root. So it's MEV. And then you've got MEV right there. So the units overall are going to be 1 over nanometers when you're done, 1 over a length.
Yeah.
And that's what you need.
I'm getting. All right, pen. Come on. There we go.
That's the one. Just get the
And what
right
is
power of
that?
10.
To the 6th.
That's what I got too. And you might want an extra digit or two there just because you're going to put that in a hyperbolic sign in a second and square it. I carried it out to 4. I went 1 point. Yeah, there you go. I rounded it to 1.384 in my calculation. And the units here are inverse nanometers, right? Okay, now multiply that by the length of the barrier width, L.
And we would have a unitless.
You have KL is a dimensionless number. Exactly right.
That's and K or not K. L was this width here. And that's in meters. So
that's 1.3 times 10 to the minus 5th nanometers.
I
just added the exponents in my head there.
0.0014 meters. And then that's multiplied by. And
I just went the other way. Minus 5th plus minus 9 is minus 14, right?
oh, I see what you mean.
That way you convert everything into nanometers since you're already there.
Yeah, and then okay. And I have see. So that was this number is 987.
Okay, now the question is that a big number? Because you can take that number and jam it right in there. If you got a calculator that does hyperbolic signs, you're good to go. The other option, though, you have available to you is that equation I just worked up, that T is equal to, and I don't have it memorized, so I got to go back to my work here. Let's see, it was 16. And I did some manipulation on this. Your energy over V0. I factored out, I guess I factored out a V0. So I got 1 minus the energy over V0. And I'm eliminating that hyperbolic sign in favor of E to the minus 2 kappa L, where you've got kappa L. And so I think it's a little bit easier to do this. You can always go back to the original equation, but we just showed before we took such a loose that that's equivalent as long as kappa L is big. I said big, how big is big? Greater than 10 at least is what most people would use. So I would just jam your numbers into that, and I think you'll find it a pretty easy calculation.
All right. Well, if somebody wants to do that, I just found the hyperbolic sign.
You
in my
got one?
calculator.
You can do it both ways. I actually did it both ways on my work, and it comes out no difference, actually.
I would take the hyperbolic sign of that kappa L, and then I square it after it's evaluated.
Yes, exactly. Then
Okay.
multiply by 15 squared, divided through by, was it 4 times 5 times, these are by 10 in your denominator. Add 1 to that, take the reciprocal, you should get pretty much the same number. All right, finish that up and we'll meet back in the main room.
All right.
Paid that off.
Ooh.
Yeah.
But like, wait, LM dropped too?
Yeah. You both dropped in the summer, I think, right?
All right, what do you have for your transmission coefficient? Oh, you didn't take the reciprocal yet. Finish up this math here.
We did,
Wait,
Professor.
we did. It's the
3.25.
box in the bottom.
That doesn't make sense then. Hold on a second here. After you take the sign of a number, yeah, you made a math error though, right? Look right here. You just plugged in KL. You need to plug in sine of KL squared, right? In radians. And then you also dropped the 1 plus, didn't you? Which I don't think you can do here, because you're going to find that the second term there is of the same order as. By the way, this is it's a probability, so it can't be greater than 1, can it? So that's how you know that answer won't work. So put that in your calculator. Make sure your calculator's in radians now, not degrees.
Yeah.
I'm a minute.
Is that what you did? You had your calculator in degrees.
Yeah.
And so the sine of an angle in degrees, when it's that small, is the angle. That's why it came out so wrong. Yeah, your angle has to
But
be.
it's still like 10 to the power 16, even in radians. I think it's KL squared and not sine squared KL. Is that?
But you take sine of K times L and then you square it afterwards. So the order of operation is sine of K times L, and you're fine right there. Okay. There's an issue with nanometers too, though, isn't there? K times L. K times L. K times L. You've changed some things since I was here last. Okay, I think yeah, when you multiplied by your length, I think it got a little too small. Hang on. Yeah, this became a little too small. So you had told me originally, and you've erased it subsequently, that K2, I think you wrote 6.
The 10 to the power 9 is not there in that.
No, it should be like,
It's just 8.994.
yeah, exactly.
Hmm.
Let's get rid of that.
So my probability in the end is 0.981. That sound like
Yeah, I had 978. So we're
Okay.
both saying about 0.98 basically.
okay, and that
Okay.
makes more sense. It's like
Yeah,
under.
something just a little less than 1 is what you expect. All right. See why this is a frustrating mathematical problem? It looks
Yeah.
like it should just be plug the numbers in, put it in a calculator, but it's not. It's harder than that. All right. So I think just fixing up this and we're ready to go here. Listen 2 on the way back in here. Group 1, if you can pull up your solution so we can take a look at that first. And I think both groups experienced the frustration that I've seen in previous years doing what looks to be a very straight, you just plug numbers in, right? Except the relative sizes of the numbers and keeping track of radians versus degrees. And it becomes a hard, and the units, nanometers versus meters, mega electron volts versus electron volts. It just is and there's one thing, did you fix the other? Let's see. Yeah, you got it. Okay. So first group, if you want to just go on, show us yours real quick. Who's talking here?
So first we found K2, and that was just plugging in numbers, making sure to get the units correct.
And I should tell you, both groups forgot this H bar C in the denominator. Okay. Don't forget, if you're going to go with a unit for an alpha particle, a proton, or whatever in MeV per C squared, you got to clear that. And that's going to put in a factor of the speed of light in the denominator. But that's all right. It's expected. H bar C, they're tabulated on our equation sheets, on our constant sheets. Okay.
And then multiplying by L, we got 8.994 radians.
Don't have your calculator in degrees here. That's kind of the second gotcha, right?
Uh-oh. Oh, no,
Yeah.
I'm good. I'm good.
Well, if you do it the complex exponential way for the hyperbolic sign, not a problem. But when you're doing the sign here, it's got to be in radians, right?
All right, I'm good then.
8.944. When you write inverse nanometers, that really means radians per meter, and that means make sure my calculator's in radians, right? All right, continue on there, Max. They did, by the way, both groups had these same problems.
And then 1 plus plugging in stuff. And then taking the reciprocal of that, we got 0.98. So
that's a
98%.
reasonable number. And that's how you know your first attempt wasn't a huge number. You know that it's a probability. Probabilities can't be greater than 1, can't be less than 0 either. Okay. And it almost 1, reasonable chance that particle is going to get through because it has an energy of 5 MeV, which is greater than the energy of the barrier. Classically, you'd expect there'd be no chance that it wouldn't get through. There'd be 100% probability. Not quite. There's a 2% chance that it could be reflected back off of that barrier. Second group, you're up.
All right, here I go. maybe.
Yeah. Sorry, we're about 2 minutes over here, but this shouldn't take too long because I think
Well,
we got
I got my units over here. If you know, that's just multiplying by
right.
C, how they work out. We get our K here multiplied by KL. We end up with a dimensionless number. And I actually have the hyperbolic sine function in my calculator, so I did that while another person in the group did the exponential way, and we got the same numbers.
Yeah. So I think what you're saying is the calculation Max talked about for the first group looks pretty much identical. All this stuff right here, except it's a hyperbolic sine instead of just a regular sine in radians squared. And what does that tell you about the probability of getting through? It's not zero. It's just very, very small. All right, last warning, and then we're out of here. So that's the number I got too, exactly right. And you did it both ways using the approximate method I showed you and the exact method using a hyperbolic sine, and you get the same number pretty much. When you work a problem just like this in WebAssign, which will be due Friday, you may find that if you round something off early on in the calculation, like maybe right here, you only go to 1.4 maybe, as opposed to 1.3836. You need all those digits. When you start putting it into hyperbolic sines, because of the shape of a hyperbolic sine curve, the difference between going in right there and going in right there could be a huge difference in this number here, especially after you square it. And so you might be out of the tolerance of WebAssign. Don't let yourself get frustrated on that. If you've got a number that you think is pretty good for the accuracy, the rounding off that you did, just email it to me. And if it's close, I'll give you full credit for it. Don't try to match what WebAssign has. That's been another frustration with these problems. Okay. Next thing though, and when we come back Wednesday, I'm going to have a reading assignment for you. We're going to look at now three-dimensional problems. I'm going to do a square three-dimensional problem first, and then we'll get into spherical coordinates and a three-dimensional problem that looks like a hydrogen atom. And that's what's coming up for Wednesday. And that's what we'll be doing for the last, we got 2 more lectures this week. We go on Thanksgiving break. We got 2 when we come back. The last 4 topics will be just getting your feet wet on something that you'll be doing in the quantum mechanics class if you stay with this physics stuff and go on and take that class. And so we'll just get a little introductory work into what are real problems, because everything we've done so far is a one-dimensional problem. We don't live in a one-dimensional world. We live in a three-dimensional world. And as I think everybody's in multivariable calculus, so I'm hoping that you've done spherical coordinates enough to recognize those things when I talk about them on Wednesday and on Friday of this week. Questions? All right. Hey, look for the reading assignment and a reading quiz for Wednesday. And then, of course, the WebAssign, which is due Friday. And I'll put the grades in for both groups. You work through it like troopers. You did no worse than any of your predecessors with those calculations, because it's as simple as they look, they're hard to do. So good job on that. And we'll see you on Wednesday. Have a great day. We
And
lost somebody.
can I ask if we'll have an exam before our final, like another like
No,
normal
the
class
last exam will be the final.
Okay.
And it is actually Thursday of final exam week is when it's scheduled.
Okay.
It's my plan is it'll look just like the first 2 midterms. It'll focus on the material. The last thing we had on the second midterm was Heisenberg's uncertainty principle, right? And so
Right, yeah.
everything after that. So pretty much
Okay.
Schrodinger's wave equation in chapter 6, and then we're going to go into chapter 7 this week. And as much as we get through 7, that'll be the scope of the final exam, focused on that, which doesn't mean there might be,
Yeah, because it's still a
it
final.
naturally reviews itself with certain things. Okay. And so but the focus will be on everything since Heisenberg uncertainty principle on the final exam. Okay.
Thank you.
You bet. You guys have a great day.
Thank you.
One thing, who are the Amaya and Said, you want to just hang around a second? I see we lost Prince about, because you two guys are looking at the 3-2 program, right?
Yep.
Yeah, that's your goal ultimately. And Dr. Kem he's trying to make that decision to waive the differential equations requirement for you two. And the only thing that he's worried about is in graduate school, and I think the 3-2 program when you're at Columbia is a little bit like a graduate program. There's really only 2 acceptable grades in graduate school. Anybody ever told you that? Those grades are A and B. a C in a graduate school program is considered an unsatisfactory grade. And so that's the one thing I want to warn you about. In fact, both I went to Hopkins and I went to the Naval Postgraduate School. Hopkins will let you get one C in a master's or a PhD program. If you get a second C, they boot you out of the program. Okay. And Columbia is going to see your undergraduate transcript in a similar light when they're looking at accepting you in the 3-2 program. So while Dr. Kem, I think, is willing to waive the differential equations prereq, he is worried that because you'll be going into a course without the prereq, getting an A or a B, which are the only two real passing grades in graduate school, will cause Columbia to look at your transcript unfavorably. And so as long as you know that going in, I think he's willing to waive differential equations and let you take the E&M class. But realize that is there's some risk to you. You're gonna have to work hard in the E&M class because you're doing the class without the prerequisite. Okay, he doesn't want to set you up. He doesn't want to set you up to not do well. You might pass the course, but remember, for an advanced program like the Columbia 3-2, they're looking at A's and B's. Okay, and I don't know what we don't get to. I don't know what the rest of your transcript looks like, but that is something to remember, particularly in your technical courses. Okay, so that's the only thing Dr. Kem is worried about. I think he's willing to let you both in, and I think Prince wanted to take the course too. That'd be great to have the 3 in the course, but you're gonna have to work hard because you really want an A or a B. You don't want to get just a C in that class. All right. Questions on that?
I've taken differential equations in high school.
You did take differential equations in high school. Okay. Yeah. So what I'm doing with Helmholtz's equation, knowing that a sine that and you've seen you've seen
that makes sense because I've done the Schrodinger's wave equations.
Okay.
In chemistry as well in high school, so it's just
good.
Similar. So I think I'll be able to hold up next semester.
Yeah, it just don't let it slip though. That's the only risk without reviewing it. I can tell you when I taught the advanced electricity and magnetism class at the Naval Academy, everybody had already completed differential equations and then was taking a course in partial differential equations, which is, I'm going to show you some partial differential equations on Wednesday. If you're at all uncomfortable with what I'm doing on Wednesday and Friday of this week, well, I'm not saying you won't be successful in the advanced E&M class, but there may be parts of the course where you're going to have to spend a lot of time at office hours with Dr. Kem, who'll be teaching the course. Okay. But it's good to know that you've taken differential equations in high school and that you've seen Schrodinger's equation in a chemistry class. By the way, I think the chemists call it physical chemistry, don't they? They don't call it quantum mechanics. But you're studying the same stuff. That's an area of overlap between us and the chemists. All right.
Yeah, so I've learned all the the integrating on both sides to find the
okay.
In differential equations. I've learned all that in high school, so
okay.
I think I would be able to hold up.
Guarantee it's still a hard course, but at least you've seen some of the prerequisites.
And also, I've heard there's quite a bit of focus on Python as well. Like it's a very mixed course with.
It depends who's teaching it, I suppose. Dr. Kem is, I think he's competent in Python. If I was teaching it, I wouldn't be using Python at all because I don't know Python as a programming language. I suspect the last guy that taught it was Dr. Campbell before he left, and he was extremely proficient in Python, and he also taught the Python class at the time, so he kind of melded the two together. I'm not sure. That's a good question for Dr. Kem, is how much of the math will be done numerically as opposed to analytically, actually working it out on a piece of paper, and how much he's going to simulate with a problem, something like Python. That's a good question. Do you guys have academic advisors yet?
Yep. I have Dr. X.
Yeah, so I would talk the same conversation. I'm giving you one opinion. Talk to those guys too, because we all went to different graduate schools. Dr. Tech and Dr. Kaiser are probably more familiar with Columbia's expectations than I am. And so, I'm just giving you one man's opinion. Do well in E&M. I think that's a universal opinion. You'll get it from everybody. but it is certainly a course that is in some. It's more of a historical. There was always a course in almost any discipline where it was a sorting course, right? If you could do well in the course, they'd let you stay in the program. If you didn't do well in the course, they kind of encouraged you to look perhaps for other areas. And E&M in graduate physics has always been that course. And I'm not sure why historically, but it was kind of what we call the weed out course, right? It's where if you can't hang with the math and the physics, it was a course where your advisors encouraged you, well, maybe you should be an applied physics major, or maybe engineering is the way to go for you. Okay. And so that's the only thing I tell you about advanced E&M, and the risk of not doing well in it is because it is still perceived that way by a lot of people. Okay. Hey, any questions for me?
Nope. I think
All right.
we're-
I think it's great that you guys want to do it, and that just don't. The warning is, don't go into it halfway. You got to go in all in on this and do well in the course. And I think it'll be a lot of fun for you, but it'll be a lot of work too. All right.
I
thank
no
you.
doubt about it.
No doubt about it. Exactly. All right. You guys have a good day. We'll see you on Wednesday. Unless you got any other questions for me.
You too. No, that would be all. By the way, Prince texted me and he told me to tell you to excuse him from class because his internet literally vanished.
Yeah. I have to tell you, mine just exploded over the weekend. It just went down for about 9 hours. I was without the internet. I felt like it was a terrible feeling. I couldn't do any work because the internet was down. So yeah, I understand that. He could watch this because the recording, this part is still being recorded. And if he wants to watch my advice, because I think he wants to take E&M as well, if I remember right. And he may just think about some of the advice I've given you guys. So I'll send him an email.
Perfect. Thank you so much.
All right, you guys have a great
Thank
night.
you so much.
Yeah,
Take care.
you too. Take care.
Bye-bye.